when they oscillate or when they move in an accelerated fashion, they produce disturbances. Radio waves are produced by accelerated motion of charges in a conducting wire. So, if electric field is oscillating like this, magnetic field is oscillating like this. So, infrared means that hot bodies or vibrating molecules actually emit this particular infrared radiation. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to discuss a new chapter here today. In fact, this is the easiest chapter in 2nd PUC. We are going to discuss about what is an EM wave and what are the properties of EM wave. So let's get right on to it. So what exactly is an EM wave? We know that we can only see the colors that are presented towards us. We see from the visible range, that is from 400 to 700 nanometer range. So before getting all technical like this, let's see what an electromagnetic wave is. So we do know that excited particles like the charged particles, when they oscillate or when they move in an accelerated fashion, they produce disturbances. This particular disturbances is propagating in space and time, and that particular thing is known as an electromagnetic radiation, or simply we can call them as EM waves. So, electromagnetic radiation is propagated by the disturbance that is caused by oscillating charges or accelerated charges. Both can produce electromagnetic radiation. So, what exactly is this electromagnetic radiation? So, electromagnetic radiation just means that both the electric field and the magnetic field are existing in that particular electromagnetic radiation. So, how are they existing? They are actually existing in such a fashion that if this is the electric field, which is oscillating in one direction or propagating in one direction, then I can say that the magnetic field is actually mutually perpendicular to that particular electric field. So, if electric field is oscillating like this, magnetic field is oscillating like this. Okay, if I am saying that, okay, there is a disturbance that is happening in the z-axis. So, if a disturbance or a charged particle is oscillating in the z-axis, then I can say that, okay, its propagation will be perpendicular to this particular oscillation, which means its propagation of light or EM radiation will be mutually perpendicular to that particular oscillation, which means it will be propagating in the XY plane. In that particular XY plane, the oscillations of electric and magnetic fields will be mutually perpendicular to each other, which means electric field will be oscillating in one direction, and mutually perpendicular to that, the magnetic field will also be oscillating. So that is how EM waves are produced, and that is how it is propagated. That is all true. So why are we not seeing all these EM waves? Actually, we are seeing these EM waves, we are feeling these EM waves. In fact, some of the EM waves are actually passing through us right this moment. But we are not taking into consideration about the vast spectrum that is called as EM waves, or simply electromagnetic radiations. So, the only thing we can actually see in that particular electromagnetic radiation is the visible light spectrum which we see in our everyday life. We are susceptible to three colors primarily, that is RGB, or some people actually refer it to as the primary colors in our eyes also. But again, we are only sensitive to a certain region in this entire electromagnetic spectrum. So why do I say that in this entire electromagnetic spectrum? That is because if I say that, okay, this is the source of the electromagnetic radiation, let's say this is the sun, okay, and radiations from the sun is being emitted, then I can say that depending on its frequency or wavelength, both are same, because frequency is nothing but 1 by wavelength. So depending on its frequency or wavelength, I can actually categorize this particular EM waves into several segments. That is, when a range of EM waves come, or simply when an electromagnetic radiation propagates, I can say that, okay, it has several wavelengths, and it just so happens to be characterized by this particular wavelength. That is, In some places, it just so happens that the gap or the wavelength of that particular wave is large, or we can say that the frequency is comparatively less. In one particular region, the frequency is actually very low. So mu is very low. But as we move up this particular spectrum, what happens? The waves start to cram up together and their frequency actually increases, or their wavelength actually decrease as we move down the spectrum. So as we move down the spectrum, the wavelength actually decreases, and we can say that there is a special category where the wavelengths are so small but the frequency is very high. So as we move down this particular path, this particular spectrum, I can say that, okay, the frequency is starting to increase, and here the frequency is actually very high. So depending on this particular characteristic, depending on frequency or wavelength, we can actually divide this particular EM wave into several segments. So this particular several segments is mostly used by us only. We are using these particular categories in order for our collective benefit. So we are going to study about what these collective beneficiaries are, or simply what are the basic categories of EM wave on this particular spectrum. Just a gentle reminder that we can only see this particular region in the entire spectrum. So we can only see from 400 to 700 nanometers. It's actually 420 to 730, but again, we can only see a small spectrum in that entire vast region. So to kick things off, the first thing we have is radio waves. So what exactly is a radio wave? A radio wave, we all know that, okay, we use in radios. We use for communication purpose. So radio waves are actually big waves. A radio wave can reach the height of entire buildings. So that particular radio wave is actually very big. We don't see that in our daily life because it is not much interacting with us. But you can actually have radio waves that is big as buildings, but we don't actually see them. So what this particular radio wave does is that it actually is used for communication purpose. It is actually used for radio programs, radio communication, to televise and all that. So basically what radio waves are is just simply accelerated charged particles. Again, I told you EM waves are produced by accelerated charged particles, and radio wave is nothing but a part of EM wave. So we can say that radio waves are produced by accelerated motion of charges in a conducting wire. So when we accelerate any charges that is inside a conducting wire, it will produce waves, and just so happens to be radio waves. Okay, and they are used in TV communication systems, and they are generally in the frequency range of 500 kilohertz to 1000 kilohertz. Again, they are operating in the range of 500 to 1000 kilohertz. That is why you can tune your FM, you can tune your AM, and you can just modify that signal so that the exact waves you are picking up differs. So depending on that, you just changing the antenna signal, you're just changing the station, which means you're changing the frequency so that you pick up the desired channel, like 98.3, 95.2, like that. You're just picking up that signals. So I can say that FM is operating in between 88 to 108 megahertz, which means for FM radios or AM radios, when you tune in that signal, you're just adjusting the signal so that you pick up any waves in between these two ranges. And again, if you're using TVs, that is in olden days, I have to say in olden days because now nobody is using dish TVs. You had antennas. You had antennas like this, or you even had dish TVs which had one amplifier and one dish connected like this. So again, all of these were used to pick up radio signals. So this particular radio waves will come, and this particular antenna would pick up that signal, and you can see TV. If you ask your grandfather or father, then you can actually see, okay, they are used to this particular antennas, because once they are watching cricket matches or something, somebody has to go up and adjust the antenna so that the picture is very clear, because they have to pick up a specific range of frequency, or simply specific range of wavelength. So it has to be in between 54 megahertz and 890 megahertz. That is the operating condition of a TV and a simple FM radio. Now, moving down the spectrum, we have one more thing, that is microwaves. So microwaves are nothing but waves which are slightly lower than a radio waves. That is, radio waves are huge, massive, and slightly less than that there is microwaves, or simply we can call them as short length radio waves. So what do you use microwaves for? Obviously, you have already heard about ovens. Microwave ovens are there. So what in microwave ovens, what happens is that if you have a microwave oven, they produce microwaves so that this microwaves gets reflected in multiple corners and they focus on one individual point that is at the center of that particular microwave. When the microwaves get reflected enough times, the waves will actually interfere with each other, producing standing waves. So when the standing waves are produced, it just so happens that it is concentrated at a particular point. So this particular standing waves concentrate that particular microwave energy onto that particular item, which actually excites the molecules. To be technical, I can say that only the H2O molecules are excited, which means if you keep anything dry, if you keep sand inside a microwave oven, nothing will happen to that sand. If there is no H2O content, then nothing will get heated up. If you place any food item into the microwave oven, you can see that the center part is heating up, which means that, okay, it is heated up from inside. So the center part is heating up, then only the heat is spreading out, and the water molecules are actually heated up first. So that is about microwave ovens. So coming back to microwaves, we can actually say that they are short length radio waves with frequencies in the gigahertz range. So again, they are produced by special vacuum tubes. You can actually produce microwaves using special vacuum tubes. Again, you don't have to understand what a klystron is, what magnetrons are, or what gun diodes are. Basically, these are equipments that is used to accelerate charged particles. We apply a strong enough magnetic field so that it just oscillates, or it accelerates the charged particle. Magnetron, cyclotron, there are certain devices which are used to accelerate charged particles. Again, of all these equipments we can use to create microwaves. Basically, you can use gun diodes, you can use klystrons or magnetrons, you can use any of these to produce microwaves. And the basic use is, again, you can use it as short length radio waves. Because it is short length radio waves, you can use it for communication purpose. You can actually use it as radars in lower atmosphere or upper atmosphere. You can actually use it as for radar detection. So due to their short wavelength, they are used in radar systems in aircraft navigation. So you might have seen a screen like this where one object is noted like this, which is going to be a flight or something. Then there will be circles like this, and there will be a flash like this, beep, beep, beep. That is nothing but radars. They actually use short length radio waves, that is known as microwaves. So it is very close to radio waves, but it is actually in falling in the microwave category. So we call it as short length radio waves. Or simply we can say that microwaves are used for aircraft navigations or simply radar system. We can use microwave, and again we can use microwaves to heat up food items in microwave ovens. Now the next culprit in the EM wave series is nothing but infrared light. You might have seen in the Predator movies that when Predator switches his eyesight, you can see a glowing yellow bodies or purple color around it. Or for heat-seeking missiles in movies and all that, you might have seen that something will be bright yellow surrounded by red, and then by bluish colors, and then green and all that. So it is actually known as infrared detection, or simply heat vision. Heat vision is actually a loose term. What it actually means is that we utilize certain regions in the infrared region so that we pick up that particular wavelength that help us to see. So if I wear specialized equipment, specialized glasses, then I can say that I can see whatever is hot. So infrared means that hot bodies or vibrating molecules actually emit this particular infrared radiation. So hot bodies actually emit these radiation in bulk. So as more of these waves come, they appear whitish. As they get lower and lower in concentration, it appears yellowish, reddish, and then if it's completely cold, it will be black or dark blue in color. So that is what you see in the movies and all that. So we can say that it is produced by hot bodies or hot molecules referred as heat waves. So since we are detecting temperature, then we just call it as heat waves. And then infrared waves maintain important role in Earth's average temperature through greenhouse effect. So we know that Earth is having a geothermal energy. Earth is also getting radiation from the sun. So when the radiation from the sun is coming to Earth, what happens is that infrared region waves are also entering into Earth's atmosphere. These are actually absorbed by the greenhouse gases and they are trapped inside Earth's atmosphere. So they bounce around here and there and they actually heat up Earth's atmosphere, giving us the warmth we actually need. Otherwise, entire planet will be frozen like Antarctica. So again, keeping the Earth warm is the responsibility of heat waves or simply infrared radiation. It is not that infrared radiation is giving you heat. It is generally known as heat waves because it is the range in which temperature of a body is actually really visible. Okay, and they are used in IR remote switches. That is, if you use a TV remote, you might have seen that at the end of the TV remote, there is a big LED light. When you press it, it just flashes on and off. It is just an infrared pulse that is being sent to the receiver in your TV. And you can also see in movies they use infrared glasses. And again, you can use infrared in many communication devices, in switches, in recording situations and all that. You can use that red pulse, which is known as infrared radiation. So again, there are several uses for this particular EM waves. We are just listing out some of the uses and under which frequency range or wavelength range they operate in. That is the only thing we are doing right now. And the next culprit is the light we already know, that is visible light. So visible light is also known as just simply light because we see that every day. This particular visible light ranges from 400 to 700 nanometers. That is the wavelength of visible light, and we can see anything that is falling under this particular category. Before that, it is infrared region. That is before visible light, the entire, if I map out the entire spectrum, I can say that, okay, it is like this. That is, R is for radio waves, M is for microwaves, N is not there. Actually, it is a shortcut we use to remember the electromagnetic spectrum. We just imagine it as, okay, it is the name Ramani, and then we imagine it as, okay, there is some other things, that is Lux. Ramani Lux G. That is how we actually remember the electromagnetic spectrum. So by that logic, I wrote it down very quickly. So what it means is that R is for radio waves, M is for microwaves, and I is for infrared region. L is for the light that is in the visible range, and U is for UV spectrum, and X is for X-rays, and finally G is for gamma rays. So this is how we actually map out the entire spectrum, and we can say that the only part we are susceptible to, or we can only see, is actually the 400 to 700 nanometer range visible light. This is the only part we can actually see, or the only part we can actually observe. So we can actually take photographs, we can actually see objects, we can actually interact with visible light with our eyes. That is how we see the world, the colorful world around us. So actually parrots and certain other like creatures can actually see into ultraviolet spectrum. So because of that, the sky appears purple to them. For us, it appears blue because blue light is more scattering and ultraviolet scattering is not actually visible for us. But in the violet region, certain parrots are susceptible to that. So they can see the skies as purple. So again, that is one interesting thing about visible light. Just know that which frequency range it is operating in. What are the uses for this? Now, since we are moving up the ladder or down the ladder, depending on if you're talking about wavelength or frequency, I can say that the frequency is now increasing. You'll learn in the next chapter that as the frequency increases, the energy of the wave also increases. If the energy of the wave increases, the harm it causes also increases. Or I can say simply that since UV radiation is harmful for us by practical experiences, because all the doctors would say, all the skin professionals would say, all your favorite influencers would say that if you're going out in the sun, wear sunscreen. Is visible light harming us? Infrared or radio waves harming us? No, they don't have the sufficient energy for that. But UV rays can. UV rays can actually cause melanin damage, or they can actually damage our genetic material. They can actually induce damage onto our skin. So we can actually say that UV rays are harmful for us. That is because it is having a higher frequency, which means it is having a shorter wavelength. So it is damaging our skin. So because of that particular reason, we can actually use it as a weapon against the things we want to destroy. So produced by special lamps, that is, you have UV lamps to attract flies and kill them, zap flies. And its exposure can be really harmful for us. It can always even cause skin cancer known as melanoma. And again, due to short wavelength, since the wavelength is very low, the frequency is very high. Because it has very low wavelength, it can be focused and it can be used as a tool for eye surgery. If you have any eye surgery, they will focus a beam of UV rays to cut off any tissues, or to vaporize any tissues. They can actually use UV rays. And finally, UV lamps are used in water purification. When you observe certain water purifiers, they'll be written, okay, UV filtered. It means they use light waves or simply electromagnetic radiation in the UV spectrum range so as to kill germs. Because this much high energy, when it incidents any living material, it damages it immediately, killing it. So that is why we use UV light. And the next culprit is X-rays. So the funny thing about X-rays is that Roentgen is the scientist who actually found out X-rays. He actually collided a metal surface with high energy electrons, and the emitted rays were observed, and he did not know what to name them. He simply said that, okay, let it be X-ray, the unknown ray. Like in algebra and all that, we say, right, X is the unknown quantity. Like that, he named it as X-ray. But later, it stuck on and people started calling it X-rays. Then that's how we got X-rays, and it was Roentgen who actually found it. But again, so sir, the common doubt is that if UV rays can kill, X-rays can also kill, right? Of course, if you get 4 million X-rays, chest X-rays, then it will kill you. But you're not getting 4 million chest X-rays per day, right? You're getting only 1 X-ray or 2 X-ray like once in a year or something, if that happens. Otherwise, you're not getting any X-rays. So it is harmful, but not that harmful. The effect of these rays is very visible. When these X-rays pass through us, you can see that it is passing through our flesh, it is passing through our bodies, and it is going. The only thing that is slightly stopping that or reflecting it is the bones, which are highly dense. It is passing through every soft tissue in your body. So you have to understand that these are actually high energy radiations, but it is not that harmful when it is like focused and it is filtered. It is not that harmful unless the exposure is too much. So again, X-rays is obtained by bombarding a metal target with high energy electrons. I told you how electrons are produced. So again, it is used in diagnostic medicine. That is, X-rays are used in hospitals. X-rays are used in security systems, in airport checks and all that. X-rays are being used. So that is the use of X-rays, and they operate in the range that is 10 raised to 8 to 10 raised to minus 13 meters. It is just the wavelength of that particular X-ray spectrum expressed in meters. And finally, we'll be talking about gamma rays. Gamma rays, simply indicated as gamma rays, just simply indicated as gamma rays, is actually the high energy part of this entire spectrum. It is not usually seen anywhere. If you want to see or visualize what gamma rays would look like, is that a high energy gamma rays example would be When a nuclear blast occurs, for example, Hiroshima or Nagasaki, that particular place still has this particular radiation. When this nuclear reaction happens, when nucleotides are released or interaction between nucleotides happen, they release immense energy in the form of gamma rays. There are alpha rays, there are beta rays, then there are gamma rays. Gamma rays are highly energetic, which means that whatever they pass through, they even pass through concrete. They pass through concrete, they pass through bodies, they pass through bones, they pass through metal. You actually have to contain them in very dense metals like lead. Lead can actually reflect these rays to a certain extent, but again, still they are very radioactive. So when these pass through our body, what happens is that they actually damage our genetic material, like destroy our DNA, they destroy our immune systems, and our body actually decomposes and we die. That is very horrendous, very horrific to even imagine. If you want to imagine or if you want to visualize that, watch this series that is known as Chernobyl. Chernobyl is a very good example of what happens when people are exposed to high energy radiations. You can give it a watch. So again, since they are in the upper frequency range, very, very, very high frequency, which means very low wavelength, which is meaning high energy. So since it is having high energy, they are actually used to destroy cancer cells. You can actually focus them. Low energy gamma rays can actually be used to destroy cancer cells, and it is produced in nuclear reaction like an atom bomb or particle accelerators or any high energy nucleotide collisions and all that. So they are actually produced by nuclear reactions or radioactive nuclei. If you have any plutonium or cesium or something which is highly radioactive, they actually emit these radiations. Actually, if you want to see this radiations by your naked eye, you can actually use something known as a cloud chamber. A cloud chamber is simple equipment which was developed like 200 years ago or something. It is basically a chamber which is made out of glass, and you just dip alcohol like ethanol or something, and you cover that particular chamber and you place it in like visible light or something. Then you can actually see the gamma rays or the radiations that are passing through. You can actually see like lines. You can actually Google that. Just Google what is cloud chamber and you can actually see how we can visualize this emissions of gamma rays. It is very beautiful. So again, I don't want to repeat everything again because this is one of the easiest chapters, and the only thing you have to study is what is this electromagnetic spectrum, what are the different type of waves in that, what is the properties of that particular waves, and what are they used for, in what frequency range are they operating in. So that's it. And coming back to what is EM waves. EM waves, again I told you, it is nothing but it is a transverse wave. We do know that what is the difference between a longitudinal and a transverse wave is, right? I hope you know, because in longitudinal waves, that type of waves, that is sound waves or the waves which we see in deep oceans, the particles just oscillate up and down. They don't actually have energy carried on. But for transverse wave, it is much more different. The energy is actually carried on with them. So that is the basic difference between a longitudinal and a transverse wave. And again, it is a transverse wave in which electric and magnetic field are mutually perpendicular to each other. I told you, when charged particles oscillate or accelerate, they produce EM waves, which are, if a charged particle is oscillating in the Z plane, then automatically EM waves are emitted in the XY plane. In that particular XY plane, electric field will be in one direction, and mutually perpendicular to that, magnetic field will be oscillating. That is known as an EM wave, or that is the basic property of an electromagnetic radiation. So there is actually a vector representation for the EM waves, which I'll be showing you very shortly in the next session, because we are going to deal about displacement currents and some experiments. In that particular case, I'll show you what is the vector notation for an EM wave. In this class, we'll just focus on the theory, that is, what is an EM wave and how it propagates, what are the properties of EM waves. So simply I can say that EM waves are transverse waves which propagate perpendicular to electric field and magnetic field. Both are vector quantities, and it requires no medium to propagate. That is, electromagnetic radiation propagates in water, in glass, in any other material, or even in vacuum. That is, in the void space also, electromagnetic radiation propagates in all directions. That is why we say that for electromagnetic radiation, we require no medium to propagate that in. And the velocity of electromagnetic radiation in vacuum is written down as 3 into 10 raised to 8 meter per second. The velocity or the speed of electromagnetic radiation, or simply light, is written down as 3 into 10 raised to 8 meter per second. We have already seen this in the previous chapter. So again, you're all familiar with this, but still I have to tell you, okay, this is the speed of electromagnetic radiation in vacuum. So, and this velocity decreases as it enters any material medium. That is, if the wave is traveling in vacuum, it has the speed that is equal to 3 into 10 raised to 8 meter per second. But when it enters into any material medium, like the atmosphere, like water, like glass, this particular wave actually slows down. Why it slows down is higher order physics. That is because of the interaction between the electric field vector and the electrons in the particular material. But again, just understand that light will slow down as it enters into any material mediums. And the velocity will actually be lower than that of the maximum velocity that it attained in vacuum. That is one thing. And EM waves show reflection, refraction, diffraction, and polarization. These are optical phenomena which you will be learning in the next chapter, that is ray optics and wave optics. So it will show that is light will actually produce diffraction, refraction, reflection, which helps us to see ourselves, reflection. So, and polarization, which brought us cooling glasses and sunglasses. So all these effects are actually portrayed by EM waves. So since the magnetic field vector is not participating in any of these visual effects, I can say that it is actually the electric field that is contributing to the visual phenomena that we observe. That is refraction, reflection, diffraction, polarization. All this is observed only because of the electrical field. So we actually call that particular electric field as a light vector. So the electric field in the electromagnetic radiation is actually known as a light vector. Even though we represent the wave like this, in which it is mutually perpendicular to each other, the actual case is that the electric field is actually dominating and the magnetic field is actually slightly less than the electric field. They are not equal in magnitude. In real life, they are not equal in magnitude and the wavelengths are not this much clearer. It is actually as an effect of superposition of many other waves. So this is not an actual representation, it's an ideal representation. In that also, the electric field will be dominating. So that is why we call it as a light vector. Again, this was just an introduction class to EM waves. We'll see all the mathematical properties, the mathematical way of representing the speed of light in any material medium, the vector representation of waves, that is electromagnetic waves, and we'll see what a great scientist had to offer in order to produce a new type of current which we never have heard about. So I'll see you all in the next session with more information. Thank you.